We'll talk about this idea of tree diagrams now. And they're excellent ways of displaying probabilities of these multi-stage experiments. So by multi-stage, what I mean is you can break down your experiment into different parts. So different, maybe sub-experiments. That happen sequentially. Or another way to put it is in series. So there's a series of events that happen. And the nice thing about it is you can read off probabilities of events very easily from the tree diagram if you know how. So let's do an example, and while I'm doing the example, I can explain the different parts and how to determine probabilities from this tree diagram. Okay, so let's say we have the following multi-stage experiment. And it's as follows. So we randomly choose a number. We have a bag with 3 numbers in it, say, and with a uniform probability, so it's an equal chance of choosing each number 1 and 3. We choose one of the following numbers, 1, 2, or 3. And we're going to add that many white marbles to a bag that already has 2 white and 5 red marbles. For example, if I chose the number, say, 3, then I would add 3 marbles that are white to this bag. So there'd be 5 white and 5 red. If I chose, say, 1, then I would add 1 white marble instead. So it would be 3 white and 5 red. So hopefully that's clear how that first stage works. And then the second stage, once I figure out how many white and red marbles are in my bag, I am going to randomly choose a marble from that bag. So there are 2 stages in the experiment, 1 and 2. So what we can do, let me just scroll up here. We can make a little diagram. So you can either do these vertically or horizontally, whatever works best for you. I'm going to do this one horizontally. And here's the start bit. And there's 2 stages. So the first stage, if I look at it, there's 3 different possible outcomes. Or we can split it up into events as well, as long as the events are exhaustive and independent of each other. But for these purposes, I am going to do just each outcome. There are 3 of them. So I can choose a 1. I can choose a 2. So maybe I'll put a 1 here, actually. 1. I can choose a 2. And I can choose a 3. So they are the possibilities in the first stage of the experiment, stage 1. Okay. So now that I gave all of the possible events, and we just went with the outcomes, there's no more complex events than that. We're not interested in even or odd or anything like that, just the number itself. So what we're going to do is we're going to write down the probability of getting each of these events. So in this case, the probability of getting a 1 is a third. The probability of getting a 2 is, again, a third because it's equally likely. And the probability of getting a 3 is, again, a third. So I'm on this. Maybe I'll get rid of those probabilities except for one of them. But I'm just going to write the probability of getting each of those on the branch itself. We call these here the branches, and we call the end bits the nodes or vertices. Okay? So we continue on. So we have the probability of getting a 1, which is a third, probability of getting a 2, which is a third, probability of getting a 3, which is a third. So I have each of the branches labeled with the probability of getting that specific outcome or event. Now, if I choose a 1, that changes the number of marbles in my bag. So in this case, that's the yellow that we wrote down here. So there are 1 plus 2 white, which is 3 white marbles, and the number of red stays the same. There's 5. So the total number of marbles here is 8. 3 of them are white, and 5 of them are red. So if I draw a marble, there are 2 different events or outcomes, however you want to look at it. You can either get a white marble or a red marble. Now the probability, now I want to pretend like I'm here. I've already picked a 1, so I want to be given that I've chosen a 1. So the probability that if I chose a 1, that I pick a white marble, well, there's 3 white marbles out of 8 in total. So the probability is, I'll write this in blue, 3/8. And that probability is, remember, it's the probability of choosing a white marble given that I rolled a 1. So you have your conditions here as well. And the probability of choosing a white marble is 3/8. And similarly, the probability of getting a red marble, given that you rolled a 1, there's 5 red marbles out of 8 in total. Let's continue on for the other 2, white and red. Okay, so now, if I roll a 2, then maybe I'll do this one in blue up here. Then I add 2 white marbles. So now I have 4 white marbles and 5 red marbles. In total, 9. So the chances that I draw a white marble, given that I've rolled a 2, is, well, there are 4 white marbles in total out of a total number, white and red, of 9. And red marbles, well, there's 9 in total for both colors, and 5 of them are red. So that's the probability of drawing a red marble, given that I rolled a 2. So you put your conditional probabilities on the branches here. And we continue for the 3. The 3 we did. In green. So there are 5 white marbles in total and 5 red marbles. So 10 marbles of both colors. So the probability of picking a white marble, given that you chose a 3, is 5 out of 10. And the probability you chose a red marble, given that you chose a 3, is also 5 out of 10. And I wanted to give you one reminder here. And the reminder is as follows. So if you remember from conditional probability, if you have the probability of A given B, that is the probability of A and B over the probability of B. And I can multiply both sides by the probability of B, and I get the probability of A given B times the probability that B happens equals the probability of A and B. So what's cool here, if we look at this, so this is the condition, B. So I have the probability of the condition times the probability of A happening given that condition equals the probability of A and B. And that's what we have on each of these paths. If we go up this branch, the probability of rolling a 1, and then this branch, probability of getting a white, given that you rolled a 1, well, in this case, our B is rolling a 1, and our A is picking a white marble. So if we multiply these probabilities, we get the probability of doing both, of starting here and saying, well, what's the probability if you start right at the start that you pick a 1 and pick a white marble? So we can multiply these together. Multiply along your branches. So we get the ands at the end, at the leaves. So the probability of picking a 1 and, or intersection, picking a white marble is 1/3 times 3/8, and you can check that that is 1/8. So to get the and probabilities, you just multiply along that branch. So we just multiplied those together there. Let's do the next one. So the probability of rolling a 1 and picking a red marble. So that is the probability. Let me do the circle and let's say yellow, because we didn't use that yet. So if I multiply along the branches this way, I get the probability of picking a 1 and picking a red marble is 1/3 times 5/8, and there's no nice cancellation here. This just ends up being 5 over 3 times 8, which is 24. So, just to be clear, the difference between, say, this 3/8 and this 1/8, well, the probability that if I roll a 1, the probability that I draw a white marble is 3/8. That means if I start here in the experiment at node 1, given that 1 happened, the probability that I draw a white is 3/8. That's just this here. This 1 and a white, that's different. That means I'm starting back here. There's nothing given. So right at the start of the experiment, the probability that I pick a 1 and pick a white marble is 1/3 times 3/8, which is 1/8. So notice the difference there. When you have a conditional probability, a given or an if, you start further up. So you're only going along this line. That condition tells you where to start. It's given that 1 happened, so you start at the 1. But if you're not given any information, you're starting right at the start, and you got to go along the entire tree. Roll a 1, sorry, not roll a 1, pick a 1, and pick a white marble. So that's how this works. And similarly for the others, I won't do them as explicitly, but the probability of picking a 2 and picking a white marble is 1/3 times 4/9. So this is going to be 1/3 times 4/9, which is 4/27. Here we have 1/3 times 5/9, so the probability of picking a 2 and picking a red is 1/3 times 5/9, which is 5 over 27. And finally, the probability of picking a 3 and picking a white is 1/3 times 5/10, which is 5/30ths, but you can simplify that, in fact, to 1/6, so we might as well do it to 1/6. And finally, well, this is going to be the same thing. 1/3 times 5/10, or a half, is 1/6. So this is the probability of picking a 3 in the first part of the experiment and then a red in the second. And notice that none of these events are independent. The probabilities change depending on what you pick in the first bit of your experiment. So if I pick a 1, the probability that I pick a white is 3/8. If I pick a 2, the probability is different. It's 4/9. And if I pick a 3, the probability is different. It's 5/10. So note that these events aren't independent. And you can check. One thing I'll note, these are all the possible outcomes. You pick a 1, pick a white, or you pick a 1, pick a red, or you pick a 2, pick a white, or you pick a 2, pick a red, or you pick a 3, pick a white, or you pick a 4, pick a red. And all those choices are mutually exclusive. They don't overlap. There's no way to pick a 1 and pick a white and at the same time pick a 1 and pick a red. So all of these are mutually exclusive. These are the only possible outcomes for our experiment, which is multi-stage. So if you add up these probabilities here, you'll get 1. Because remember, the probability of all possible outcomes for our experiment, and here's all of them. Let me put boxes around these. That looks a little better. If I add up all of those guys, I get 1. So note the sum, and we'll use this Greek letter sigma to mean the sum of all leaf probabilities. Remember, the leaves are at the end of the branches, so they're right at the end. So the sum of all the leaf probabilities equals 1. And you can check that. So an eighth plus 5/24, you do a little side calculation, you'll find that that is indeed a third. 4/27 plus 5/27 is another third. A sixth plus a sixth is a third, and 3/3 is 1. So that's something to note, and it's a good check that you did your calculation correctly. So all of these should add up to 1. Let's continue, and let's do a few problems here using this same diagram. So let's do the first one. Some of these you can just read off, and others you're going to have to be a little more careful, but that's okay. So the first one is, what is the probability that you, let's say, pick a white, given that you roll a 3. That one's very easy. We can just literally look that up in our table. So we're given that we roll a 3, so we start here, and the probability that we pick a white, we just go along the branch. There it is. There, it's 5/10. So those are the answers, I guess, in blue. Okay. The second one, let's do the probability that you, let's do just pick a white marble in total. Well, this one's a little harder, but if you think about it the correct way, it's not too bad at all, and the tree diagram helps us out here now that we have it done in total. Well, remember, there's only 6 possible outcomes for our experiment. There's no given here, so we're starting right at the start. Okay. So, the ways we can pick a white is we can either pick a 1, then pick a white, so 1 and white, or it can be 2 and white, or it can be 3 and white. And remember, all these guys are mutually exclusive. So this is going to be, it's going to be the probability that we have a 1 and a white, plus the probability that we have a 2 and a white, plus the probability we have a 3 and a white. And we have all of those probabilities. We just have to add them together. So this is going to be 1 and a white was an eighth, 2 and a white was 4/27, and a 3 and a white was a sixth. And you can check that a good common denominator is 216. That's the lowest common multiple of 8, 27, and 6. So let's convert these all to over 216. Sometimes the fractions get a little big, but that's okay. And I multiplied 8 by 27 to get 216, so we'll multiply 1 by that as well. So this is 27 over 216. 27, I multiply by 8 to get 216. So 4 times 8 is 32. We're just doing equivalent fractions here. And I multiplied 1/6 by 36 to get 216. And 1 times 36 is, of course, 36. I add those together. 27 plus 32 is 59. 59 plus 36 is 95 over 216. And that equals, if you want it as a percentage rounded to the nearest, let's say, tenth of a percentage, that's going to be 44.0%. So in this experiment, the chances that I pick a white marble, starting at the start, are around 44% there, 95 over 216. And we might as well do what's the probability of picking a red. You could do the same thing. You could say, all right, well, it's a 1 in a red, plus a 2 in a red, plus a 3 in a red. You would get the right answer, don't get me wrong. But we already have some information. We know the probability of picking a white. And there's kind of only 2 things you can pick in the last bit of our experiment, a white and a red. They're mutually exclusive. So that is the same thing as a probability of not picking a white, which is 1 minus the probability of picking a white. So it's 1 minus 95 over 216. And we can change that to 216 over 216 if you like, and you would get 121 over 216. Which is, you can probably see this is going to be around 56%. Let's do one more quick example here. Let's do the probability of, let's say, picking a 1 or picking a red marble. And we've already done some of this work. So let's use our formula for the probability of OR events. So this is going to be the probability of picking a 1 plus the probability of picking a red. But we have to subtract the probability of doing both, picking a 1 and picking a red. And these are kind of easy to see, the probability of picking a 1. Let's go up here, scroll up. This is in the first stage of our experiment. So that's just a third. The probability of picking a red, I've already calculated that. That's 121 over 216. And the probability of picking a 1 and a red, that's 5 over 24. That's right here as well. So we can put all of them in. So it was 1/3, 121 over 216, and 5 over 24. Okay, let's scroll up here, or down. So it's 1/3 plus 121 over 216 minus, this was 5 over 24. Let me scroll up and check that just to make sense. Or to just make sure, I mean, it is 5 over 24. Again, let's convert these to 216 as a denominator so I can do some easy subtraction. So I'm going to multiply top and bottom here by 72. The least common denominator of 3, 216, and 24 is, of course, 216. 216 already has a denominator of 216, and 24 I'm going to multiply by 9 to get 216. And you can use the prime factorization of 216 to kind of help you figure out what you need to multiply. So they're going to multiply by 9 on top and bottom. So we get 72 plus 121 minus 5 times 9 is 45 over 216. They all have the same denominator, so I can add and subtract just with the numerators. And I get 148 over 216. And if we were to simplify that, we would get, I think there's a factor of 4 in there. Divide top and bottom by 4. You would get 37 over 54, which is about 68.5% rounded to the nearest 0.1%. So let's recap, just to make sure we understand what's happening here. Let me scroll down yet again, and let's recap. So, tree diagrams have multi-stage, or 4 multi-stage experiments. So, you put, here's stage 1, and you have your choices here. Let's say they're A, B, and C, but if you only had 2 choices, you just have A and B. If you had more than 2 choices, you would have that number of branches coming from that starting node. And then, from each of the outcomes in the first stage, you're going to have more branches to each outcome in the second stage. Let's call them X, Y, Z if there were 3 of them. Maybe there's not. Maybe there's 2 or 4 or whatever. You just put how many there are. So, remember the probabilities that go on the branches for the first stage of the experiment are just the probability of doing that. So this one would be the probability of B. The probabilities that go on the branches in the second stage are given that the first stage has happened. So here you would put the probability, for example, that Z happens given that B happens. And the probabilities that you put on the leaves are just these probabilities multiplied together. So it is the probability that if you're starting at the start, that both happen. In this case, it's the probability that B happens and Z happens, and that is the probability of B times the probability of Z given B. And that's similar to for all of the other paths you can take here. So you can fill out the entire tree diagram and then use your probability skills and probability knowledge to answer a whole whack of probability questions. I will say, be careful, just make a note. Be careful with the setup. Sometimes the result of the first stage affects what happens in the next. And similarly, for if you had multi-stage experiments, I guess this we can write down as stage 2. If you have more stages than 2, the result of what happens in stage 2 might affect the probabilities in stage 3, for example. So, be careful when you're setting up the experiment to make sure you're taking that into account. Remember that these are conditional on what happens in the previous stage.